Welcome back. Let's continue with where we left. So yesterday you have calculated the value of W, right? So main application I want to tell you here is we will apply this for what is that? Using our first law of thermodynamics because the value of Q was also asked. So let me just give you a hint. You can calculate yourself. So what is first law of thermodynamics? Delta U is equal to Q plus W, isn't it? And what's the value of W you got? You got it as minus 8030 point something, isn't it? Now, being isothermal process, for isothermal process, what did we say? Delta U is equal to 0. So substitute delta U is equal to 0 in this. 0 is equal to Q plus W. So Q will be equal to minus of W. So whatever value you got yesterday for W, substitute that and minus of I believe it was minus 8030 something, isn't it? So minus of minus, your value of Q will become positive in this case. Okay. So I believe you can do this. Got it? So the next important thing we are coming up here is the concept of enthalpy. Now, what is enthalpy? Enthalpy is called as the heat content of a system at constant pressure. So we also denote it as QP. That's another way. And by and large, we use delta H. Okay. So basically, H is enthalpy. H is equal to P plus, H is equal, H is equal to U plus PV. So here this is basically we use a delta H concept mainly for chemical reactions. And chemical reactions are always carried out at constant pressure conditions. That's why you call this as a heat content at constant pressure. So now, the first state 1, let H1 be U1 plus PV1 because P is constant there and H2 is U2 plus PV2. Then what is delta H? Delta H is H2 minus H. Now, H2 minus H1 in this case will be, now substitute that. So what shall you use? Subtract. If I call this as equation 2 and call this as equation 1, 2 minus 1 operation you do. So delta H will be equal to U2 minus U1. What is U2 minus U1? It's delta U plus P into V2 minus V1. What is that? It's P delta V. So this is how we get the equation delta H is equal to delta U plus P delta. Got it? Now, another way of interpreting this is, we know for ideal gas, PV is equal to nRT. So when I take the change in volume taking place here, keeping pressure constant. So P delta V is equal to delta NG/RT, where delta NG is number of moles of gaseous products minus number of moles of gaseous reactants. All in gaseous state specifically. So this is what you would apply mainly for equations, mainly for chemical reactions. So substitute delta Ng in this R and T. So this will, you can rearrange this as delta H is equal to delta U plus delta NgR. This is another important equation we have with this. Okay, so simple. So put delta Ng is equal to 0. That means number of moles of products and number of moles of reactants are same. So let me take an equation something like this. So you have 2HI is giving H2 plus I2. So what is happening here? In this case, number of moles of reactants will be 2. Number of moles of products will be 2. So put together, what do we get? You will get delta Ng. Now in this case will be 0. It's 2 minus 2, which is 0. So in such case, what will happen? Delta H is equal to. So whenever delta Ng is equal to 0, delta H will be equal to delta U. Got it? Now, the second case I will take when delta Ng is Greater than 0. What do you mean by delta Ng is greater than 0? The number of moles of products will be greater than number of moles of reactants. So let me take an example. What will happen in such case? When delta Ng is greater than 0? What will happen, Evelyn?
Ma'am, can you repeat, ma'am?
See, this is the equation. Delta H is equal to delta U plus delta Ng RT. Now, when delta Ng, what is delta Ng? Delta Ng is number of moles of products minus number of moles of reactants. Only in gaseous state, not in any other state. Got it? So, when delta Ng is equal to 0, substitute delta Ng 0. What is it? Products will be equal to reactants. Right? So, delta H will be equal to delta U. And when delta H is greater than 0, number of products will be greater than number of reactants. So put delta Ng is greater than 0. How is delta H, delta U related? Isn't it delta H will be delta U plus delta NgRT? Delta Ng is positive. So will delta H be greater than delta U or less than delta U? My question is that.
Ma'am, I didn't understand the question, ma'am.
Okay. So I want you to analyze this. What is delta? I'll give you an example. But without example also, are you in a position to take it? See what is happening in the example I've given, 2Hi giving H2 plus I2. All these are in gaseous states. How many gaseous reactants are there? 2. How many gaseous products are there? 2. Can you see in this Hi?
Yes, ma'am.
Now, what will be delta Ng in this case? Number of moles of products minus number of moles of reactants. What will be delta Ng value? 0. Do you agree?
Ma'am, how is it 0, ma'am?
How many products are there, Evelyn?
Okay. 2. Okay.
Now, what is delta Ng formula? Number of products, number of moles of products in the gaseous state and number of moles of reactants in the gaseous state. What shall be the difference now, delta Ng?
0.
0. Can you conclude now delta Ng is 0? Now, if you substitute delta Ng 0 in the equation, what will you get?
Number of moles of product is equal to number of moles of reactant.
No. Delta Ng is 0, you substitute in the equation for delta H. Substitute delta Ng is 0 in the equation delta H is equal to delta U plus delta Ng RT. Substitute, no? Delta Ng is 0. Do it. More than virtually seeing, I would love to, you put it on the paper and see. Delta H is equal to delta U plus delta Ng RT. Put delta Ng is equal to 0, what will happen?
Delta H is equal to delta U plus RT.
When you put delta H is 0, how will you get RT, Evelyn?
Only delta U.
Isn't it? So, now what is a new relation we are getting just because delta Ng is 0?
Delta H is equal to delta U.
Can you get that? Okay. Now, the next case, that's a first case study. Second case study is put delta Ng is greater than 0.
Yes, ma'am.
That means delta Ng is positive. So, my question was, will delta H be less than delta U or greater than delta U? Think over. Yeah, good morning, Jerome. So, just you also consider that. So, will delta H plus, when I say is equal to delta U plus delta NgRT. Now, delta Ng being a positive value, will delta H be greater than delta U or less than delta U? When I'm giving you an example, I can only predict whether delta Ng is less than or greater than. But this is something that you should be in a position to calculate. I'm telling you delta Ng is 0, is greater than 0. That means, what will happen to the second term? Is it positive or negative?
Positive.
Now, delta H is delta U plus of some positive value. So will delta H be greater than delta U or less than delta U?
Greater.
Yeah. So if delta Ng is greater than 0, delta H will be greater than delta U. This is something that you should be in a position to analyze. So coming with an example, so consider this example. PCl5 is heated to give PCl3 and Cl2. All are in gaseous state. How many products are there? All I'm telling you in terms of moles only. Products PCl3 and Cl2, there are two. PCl5 is 1. So what is the value of delta Ng for this? It's
One.
equal to
1.
2 minus 1, which is 1. It's a positive. It's greater than 0. So for this equation, what is the relation between delta H and delta U? Delta H is greater than delta. Is that clear? Is that understandable? Yeah. Now what will be the third case? What will be the third case? Third case is, come on, you only tell me. First we saw delta Ng 0, delta Ng greater than 0. So what shall this be? Delta Ng is
Less than
less
0.
than 0. So in such case, that means number of moles of reactants. See, all are gaseous. Throughout this chapter and throughout the next chapter also, remember in equilibrium chapter also, we will consider gaseous only. And in no circumstances we will take number of moles in solid, liquid or any other aqueous states. It's gaseous only we consider. Okay, because we are taking a system of ideal gases. Got it? So number of moles of reactants less than number of moles of products. Now, what is the relation between delta H and delta U now? So when you put delta H is equal to delta U, what will be the second term? Second term will be positive or negative. If I put delta Ng is less than 0, that will become negative. So delta U minus of something will come. Isn't it? So when you say delta U minus of something, so overall what will happen? Delta H is less than delta U. Is that clear? Taking an example, nitrogen plus hydrogen giving ammonia. Got it? So how many moles of reactants? 4 total. 1 plus 3 and 2 moles. So isn't it number of moles of I'm sorry. I'm sorry. Let me take back. Products is less than reactants. Yeah. This is a okay. Because delta Ng is Np minus Nr, no? Np minus Nr is less than 0, is Np less than Nr. So the equation is correct, but this is something that no, please correct it. So number of moles of products is less than number of moles of reactants. It goes very well with this condition. So in case of formation of ammonia, we call this equation as formation of ammonia. Formation of ammonia, delta H is less than delta. Got it? Is that clear now? So delta H, it's something, whatever conditions we have given for Q, the same thing holds good. What did I tell? QP is, it is the heat content at constant pressure, which is nothing but delta H itself. So what is the condition for heat we gave? What is the sign convention for heat we gave? The same will be the sign convention even for delta H. So QP or delta H, when I take, if it is positive, that means it is endothermic. And if it is negative, it is exothermic. Okay. Is that clear? So we will see now different types of enthalpies. I will explain you each type of enthalpy and then I'll come back to what is enthalpy of a reaction. See, what is enthalpy basically? It's mainly the energy term we are using or the heat content we are using by and large for chemical reactions. Okay. So how many types of chemical reactions are there? How many types of chemical reactions are there? Can you name few chemical reactions you know? I ask you for types.
Reaction.
Come again?
combination reaction,
Okay.
decomposition reaction,
Okay.
displacement, double displacement, oxidation
Okay.
reduction.
So many, right? And see, that's a different story. When you go to redox reactions chapter, you will learn that some of the reactions you have named are already redox reactions, like combination, decomposition, displacement, are all they most displacement. All these are redox reactions already. Now, apart from that, you have some reactions like combustion reactions, right? So many changes do happen. Even in physical changes, you observe that there is a heat absorption and heat evolution taking place. So wherever there is a heat evolved or liberated, that's where your delta H is coming into play. Is it clear? Any process, you call it as exothermic, endothermic. Let it be a physical change or a chemical change. Any of this. Where and all you see a change in heat. That means heat absorption or heat evolution. There and all, our delta H will play a vital role. Is that clear? So, I want you to understand the term standard. What do you mean by a standard state? This is something that you have to, register strongly in your head, that don't overlap standard state to STP. That's very, 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 very important. This is where most of the students tend to go wrong. So, what is STP? I think yesterday I told you what is STP. What are the conditions of STP? Quickly.
Zero degree Celsius and 1 atmospheric pressure.
Okay, so that means I can take it. Okay, 0 degrees Celsius or 273 Kelvin, 273.15 precisely. Okay, and 1 atmosphere. I mean, actually, we take it 1 bar. Okay, there's a subtle difference between bar and atmosphere. Okay, and what is a standard state? There is a difference. STP, we call it as standard temperature and pressure. But when I take standard state, the temperature pressure conditions at standard state is different. So when I say standard state, basically standard state refers to the state, okay, it is where substances actually exist in pure form. So for example, water is there. What is normal pure in pure state? How will water exist as? Solid, liquid, or gas?
Liquid, no?
Liquid, isn't it? So at what temperature will it exist as liquid? Approximately. Okay, when will it exist as solid? When will it exist as gas?
When sublimation takes place, no?
Will water sublime?
No. No, ma'am.
Ma'am, it's solid at 0 degree Celsius and
So
gas.
in the form of ice, it's solid. Simple. Put it this way. And in the form of steam, it is a gas. Am I right? When will this ice be? Now coming to your point, Evelyn. When will it exist as ice? 0 degrees Celsius. When will it exist as steam? 100 degrees. I mean, less than 0 degrees, less than 100 degrees. It's purely in these states. Not less. Greater than 100 degrees, it will be purely in these states. Right? Now, where is water exist as a liquid? On average, I can say that at room temperature, it is liquid. On average. So how does carbon dioxide exist at room temperature? Solid, liquid, gas.
Gas, ma'am.
Gas. Hydrogen. What
Gas.
is the physical state you give? Hydrogen, oxygen, all this.
Gas, ma'am.
Or when I give you carbon, what is the state you give? Carbon is a solid. So hydrogen, oxygen, all these are gases. See, every substance will have the corresponding melting point or boiling point. Of some of them sublime, they have a sublimation point. But at room temperature, how do they exist? So we refer to the average room temperature is that temperature where substances are existing in the original form. Are you getting it? And what is the average room temperature? I'll take it as 25 degrees Celsius. See, today it can be 28, tomorrow it can be 22, and on a hot summer days you will see it's about 30. That's different. Or on average, what we see globally. You cannot compare. When you go to polar regions, it's different. When you go to desert, it will be different. So on average, what's the room temperature? 25 degrees Celsius, or we take it as 298 Kelvin as the temperature at standard state. This is something that you have to remember. Don't overlap this with STP temperatures. STP is totally different. Standard temperature condition is 0 degrees only. Whereas standard state is 298 Kelvin. Oops, 1 bar. Clear? The pressure remains the same. Got it? That will remain the same, but temperature variation is there. So whenever we refer to standard state, this is a condition of standard state. Okay? And when you say STP, it's 0 degrees Celsius you have to take. Otherwise, the pressure is the same. And the notation that goes is, we generally use it this way. Okay? Maybe in your textbook, no, it appears like theta. The way the notation is appears like theta. It's accepted. You can write it as naught, as a degree sign. It's very well accepted. Don't have to worry about it. It's easy to write. So we will write it as delta G naught, delta S naught, delta H naught. That naught is indicating that it's at standard state. So when I write simply the difference between delta H and delta H naught is, we call this as standard enthalpy. Whereas this is simply enthalpy, not at standard state. That's a difference. So you should be in a position to identify the notation. Is it given as naught or it's simply without it? Clear? This is a very, very important distinction you have to know. When you're reading a question, please observe that. How is it interpreted? Is there a naught there, or, that is missing? Is that clear? Now, we will see different types of reactions, as I told you. So the first reaction we have, 1 second. Yes. Enthalpy of formation. I would like to go for this and then I will go with the remaining. Everything is there in this, okay? Enthalpy of formation. So when I mean formation, please note the symbol. Symbol is important. That will tell you, give you the entire, meaning. Suppose I'm writing it as delta H naught F of NaCl. Delta H naught F of CO2. Delta H naught F of CH3OH. I'll write this. This is how the notation will be given. So from the symbol, you should be in a position to interpret. You should be in a position to deduce the equation. That's a very, very important exercise. If you go wrong in that, your entire numerical will go wrong. This type of question is almost probable or certain, whether it's in your PU boards or it is in any competitive exam. This is one of the important chapters and questions from, we call it as a thermochemistry, totally, this branch. Wherever you're doing the delta H calculations, from reactions, it's called as thermochemistry. Almost probable, certain question, whether it's competitive or both. Keep this in mind. Unless or until you're thorough with the symbols and you know to interpret it, you will be able to solve the questions. So let's come to the meaning. What is standard enthalpy of formation? So formation of 1 mole of a compound from its elements. So I have written delta. Value will be given. Don't worry about it. For everything, values will be given in the numericals. So when I'm writing delta H naught F NaCl, what is the meaning? It is enthalpy, standard enthalpy of formation of NaCl. That is actually the verbal meaning of this delta H naught NaCl. Okay. Now, what's the definition? So, formation of 1 mole of the compound. 1 mole of which compound in this case, if I say NaCl? It's formation of 1 mole of NaCl from its constituent elements. So, what are the elements present in NaCl?
Sodium and chlorine.
Sodium and chlorine. Very good. So, it is formation of 1 mole. So, basically, Na plus Cl2 is giving NaCl. And you know, this kind of equations, what you write are called as thermochemical equations. Okay. And you know, whenever you write this thermochemical, it's a balanced equation only. We will give the delta H value. We will give the physical states. Physical states are mandatory. NaCl is a solid. Chlorine is a gas. Sodium is a solid. All right. Now, formation of 1 mole. What you should do is balance this equation as per 1 mole of NaCl. Don't balance it the usual way you do your stoichiometric balancing. See, stoichiometric calculation is, of course, it is a stoichiometric equation, but you have to specifically balance according to 1 mole of NaCl. So, if I want 1 mole of NaCl, how should I balance? How many moles of, I want 1 mole of this. So, how many sodiums should be there on the left side?
1.
1. How many chlorines should be available?
Half.
Exactly. Half of Cl2. That will make 1 atom of chlorine. So, I'll balance it as Na plus half Cl2 giving NaCl. Normally, how would you balance it? You would say 2 Na plus Cl2 is 2 NaCl, isn't it? That will be your normal balancing. You know, because normally when balancing, we don't use this halves or we don't use any fractions or decimals. We make it as an integral, numbers only, the coefficients as. So, but here we are balancing based on the meaning of standard enthalpy of formation. This plays a vital role. Okay? Absolutely right. So, this refers to what? Enthalpy of formation. So, whatever delta H is associated with this particular equation, we call it as standard enthalpy of formation of NaCl. Is that clear? Now, let's go with CO2. Come on, just give me an equation for CO2. What shall be the equation? Because this is a very, very important exercise, students. Without which you will not be in a position to answer any question. So, what does CO2 contain? What are the elements in CO2? Let me work backward.
Carbon plus O2.
Carbon plus
O2.
O2. Carbon is in which state?
Gas.
Is it a gas?
Solid.
Yeah. Oxygen?
Gas.
Yes. So, now, is this equation balanced as per 1 mole of CO2?
Yes.
Yes. So, what is the delta H associated with this called as? So, is it a reaction? It's a reaction. So, what is the heat content that is involved with this reaction? That is only delta H. Okay? Because during a reaction, pressure is kept constant. So, heat content at constant pressure is what? Delta H. So, that's why for every reaction, we give the corresponding delta H. So, what is this? It's the delta H of formation, F for formation of CO2. Now, please design your equation for CH3OH. CH3OH. What do you think CH3OH should be? Okay.
CO2 plus H2O, ma'am.
Okay. Read the definition again, Jerome. It is formation of 1 mole of a substance from its elements. So, what are the elements in, what do you call this compound?
Methanol.
Methanol. Methanol. Methanol is a liquid. Okay? Yeah. So, what are the elements present in this?
Carbon, hydrogen, oxygen.
Exactly. Just come from the elements only. Don't go for alternate methods of preparation. We are not doing that. See, there could be number of ways the CO2 can be prepared, Jerome. Number of ways methanol can be prepared. Number of ways even NaCl can be prepared. We are not bothered about every method. But as for the symbol, what does a symbol tell you? Symbol is formation. According to the definition, what is formation? We have to design an equation such a way that 1 mole of the substance is prepared from its elements, its constituent elements, not anything else. So stick to the symbol, stick to the equation, stick to the definition. So they all should sync up. So what is it? C plus H2 plus O2, right? Now, balance this equation according to 1 mole of CH3OH. Come on. So carbon is a solid, hydrogen is a gas, oxygen is a gas.
Carbon plus 2H2 plus half O2.
Exactly. Is that clear now? Isn't it perfectly going with 1 mole of CH3OH? This is what you mean by enthalpy of formation. It's not that you create some random equation. You have to create an equation based on the meaning that delta H naught F is giving you. Based on its definition, you're creating the equation. This is something you have to be very clear about all these, delta H, what we are going to create for different reactions. Based on the nature of the reaction, based on the nature of the notation we give, your equation will change. Clear? Got it?